Hey everyone, Jason here, and this week we're going to be talking about heat transfer. Alright, let's get started with the material this week. If you remember from units and properties, temperature is a measurement of the energy in a substance. The higher or lower the energy, the hotter or colder it is. So heat is that energy in motion. That means that something is driving the energy in a given substance to move from one spot to another. And that thing is just the temperature difference. Heat transfer is all about how heat moves based on the temperature difference. Now we've already looked at several heat transfer concepts. You've covered conduction, convection, and radiation in a previous class. Now if you'd like to review the methods of heat transfer, I've included a nicely done video by Mike Samatano on your activities page. So another concept you've already been exposed to is the idea of sensible heat transfer versus latent heat transfer. Really, our discussion on the poultry problem covered both. The viral problem solver used the specific heat capacity equation, which only covered the sensible heat addition. What he missed was the enthalpy change due to the heat of vaporization. Now in both those equations, we are taking the physics perspective of looking at an overall system. If you remember from one of our first weeks, we can define a system as a very large interconnected series of components and pipes and stuff, or we can define it as a smaller component, such as a heat exchanger, or even a cross-section of a smaller part of a system, such as a fuel pellet. You'll see that this week. The fuel pellet transfers heat through the helium gap to the fuel cladding, and then to the laminar boundary layer of the coolant, then to the bulk coolant flow. And that's one of the things you're going to need to know coming out of this week. What I want to cover is that as a physics class, we get to look at the overall system, even if it's narrowly defined. And we really only consider the difference between the start and the end of a process. For example, we can use the delta T, the difference in temperature overall, as a generalization of what is happening within the system. Your text goes through some examples of how the equations we use are derived. You don't need to know the derivation of those. It's a second and third year materials thermo way of saying that what's going on in between 2 points is more complicated than we're presenting. But in physics, we don't care. We won't be calculating at a temperature at a specific point within the fuel pellet or within the cladding, right? Or we won't be comparing the difference between a 0.5 inch into the coolant channel and a 0.1 inch into the coolant channel. We only care about what happens overall. So we generalize with delta T. Just know that the larger the temperature difference, right? The larger the temperature difference, the larger the rate of heat transfer. As that heat is transferred, that temperature difference goes down, and so the rate of heat transfer goes down. But again, we're going to look at the temperature difference between the fluids going in and the fluids going out. So to that end, the PowerPoint jumps right in on solving some problems. The first is simply calculating the rate of heat addition given a temperature in, given a temperature out, given a flow rate, and a specific heat capacity. It's pretty convenient that these properties exactly fit the MC delta T equations, so that first one should be pretty easy. All the units work out with no weird conversions. We do the same with a phase change. One point that is often confusing is that the idea that we can't use the MC delta T equation for a phase change, but we can use the M delta H for a sensible heat addition, as well as the phase change. So if you were to reattempt the poultry problem, you could use just one equation as long as it's the rate of heat transfer, the Q dot equals the mass flow rate times the difference in enthalpies. The PowerPoint gives you an example problem where you have reactor coolant, which means water. You have to understand that that correlates, right? Coolant means water. Enters the core of a reactor at 535 degrees Fahrenheit as water and exits at 552 degrees Fahrenheit as a saturated vapor. The problem looks confusing at first because it gives you a specific heat capacity and the H sub Fg, right, for the enthalpy difference between the saturated water and the saturated steam. The point of giving you those properties to show you that you can solve the problem by first solving the sensible heat addition using the MC delta T equation, then adding the heat addition for the phase change, I think it's 638 that it gives you. However, to prove to yourself that you can just use the phase change equation, I recommend solving it both ways. the PowerPoint only solves the phase change version. Either way gives you the same answer. Now let's talk about the rate of heat transfer across a boundary in a component or system. Your PowerPoint has several slides that help show you how the overall heat transfer equation comes about. It uses a generic or overall look at each of the terms. Like we discussed before, we're able to consider the start and the end of a process and not worry so much about what happens in between. It's the same with heat transfer in a heat exchanger from one fluid through a tube wall to another fluid. We're going to generalize it a bit. The thing we have to realize, assuming no losses to ambient and no frictional losses, is that the rate of heat transfer for one side of the heat exchanger is equal to the rate of heat transfer on the fluid on the other side of the heat exchanger. And when I say one side and the other side, I mean one fluid to the other fluid. For example, if we have a heat exchanger that uses a cool fluid to cool a hot fluid, the rate of heat transfer of the cool fluid equals the rate of heat transfer of the hot fluid, even if they have different mass flow rates, specific heat capacities, enthalpies. The Q dot hot equals the Q dot cool. So whether we're using the equation with specific heat capacity or the equation with the enthalpies, one side equals the other. To help visualize this, if you have two fluids, one hot and one cold, going through a heat exchanger, right, whether they're parallel or cross flow or whatever, if the hot fluid has a higher mass flow rate than the cooler fluid, then the change in temperature or the change in enthalpies of the hot fluid is less than the cool fluid. Basically, if the hot fluid is spending less time in the heat exchanger because it has a higher flow rate, then less heat is removed. And this can be shown with your equations. Given enough information about one side of the fluid, you can extrapolate whatever information you need from the other fluid. If I give you a mass flow rate and an inlet and outlet temperature of one fluid along with the inlet and outlet temperature of the other fluid, you'll be able to figure out the mass flow rate of the second fluid. All right, I've been rambling long enough. Let's review some highlights real quick. Heat is energy in motion as a result of a temperature difference. While we have three modes of heat transfer, conduction, convection, and radiation, we're really only worried about conduction and convection, and mostly conduction. So you can ignore that whole radiation equation in your PowerPoint. While log mean temperature difference is more accurate, we'll simply be using the difference in temperature or the difference in the enthalpies. We're going to simplify it. The overall heat transfer coefficient is the measure of the ability of a heat exchanger to transfer heat from one fluid to another. All right. With all that out of the way, let's talk real quick about your quiz this week. So this week's quiz will cover a couple of the problems from your PowerPoint. You'll calculate the rate of heat transfer when given the properties of a fluid, similar to that first one. You'll have to pay attention to whether there's a phase change involved or not, so you're figuring out which equation to use. And for some there will be, for some there won't. You'll have to describe or define each of the three modes of heat transfer, the conduction, convection, or radiation. You'll have to solve a problem or two involving a hot fluid and a cool fluid in a heat exchanger, whether I'm having you find mass flow rates or an outlet temperature or whatever. There's a slide in your PowerPoint that shows a fuel pellet, the helium gap, the fuel cladding, the laminar layer, and the bulk coolant flow. You'll have to describe that process and identify which heat transfer mode applies at each point. In fact, one thing to think about is, why is the mode of heat transfer across the helium gas gap conduction and not convection? I might make that extra credit, not sure yet. Besides that, you'll see some review questions. I'll probably pick some high-miss questions, so make sure you're reviewing your old quizzes. Make sure you ask your questions in the Questions for the Professor discussion post. Contact me if you have any concerns. I hope everyone has a great week. Thanks. It was awful, wasn't it?
No, you did good.
Look good?
Now it's good.
Hey everyone, Jason here. The problem looks confusing at first because it doesn't give you a specific heat capacity. It's not true. A really
This
nicely done bind.
I'm talking 10 miles an hour, right?
I don't,
I need to be able to pause this from back there somehow.
you don't have a remote for this?
For the
For that.
Chromebook? Nope. I did try hooking this up to the Chromebook with Bluetooth, and it does, but pressing the thing changes the volume.